Hi, in this video we are going to discuss regression model with multiple regressors or multiple independent variables, and this is the general form of this model. So in this case we assume that the value of y, which is the dependent variable, will depend on the value of variable x1 and variable x2. So basically x1 and x2 stand for two different independent variables. So when it comes to assumptions which have to be met in order to design such a model, the first 6 assumptions should be familiar to you at this point. We already discussed them when we analyzed two variables regression model, and we have 2 new assumptions which are specific for the model with multiple regressors. So first of all, there should be no exact collinearity, and second, there should be no specification bias. So let us start with exact collinearity. So speaking informally, exact collinearity occurs when the sum of two variables composes some constant value, or for instance when you can calculate the value of one of the variables as the linear function of the other variable. I will give you some examples. So first, you can consider proportion of males and females in population. So the sum will be equal to 100 always, and you can always express proportion of females as the difference between 100% and proportion of males. So in this case, only one variable can serve as the regressor. The second example, number of hours devoted to sleep, work, and leisure. The sum will always be equal to 24 hours, which means that only 2 out of 3 variables mentioned above can serve as regressors. Dummies for male and female workers. So the sum will be equal to 1. I believe it's kind of intuitive, because when the worker is male, automatically the worker is not female. So you will have 0 for male dummy, 1 for male dummy and 0 for female dummy, and vice versa. If the worker is female, you have 0 for male dummy and 1 for female dummy. So in this case, you will deal with exact collinearity, and actually that's why I mentioned that the number of dummy variables inserted to the model should be smaller than the number of categories. Because if you design a dummy for each category, for instance, like in this case, male workers and female workers, you will deal with exact collinearity. So now you know why the number of dummies should be smaller than the number of categories. So there is a short note on collinearity and exact collinearity. So please keep in mind that exact collinearity occurs when there is exact linear relationship between two variables. So for instance, proportion of females in population is equal to 100% minus proportion of males in population. However, the independent variables can be correlated, of course, only up to some extent. I will get back to this in a second, as long as there is no perfect collinearity. For instance, in GRETL, you can check collinearity by designing correlation coefficients matrix, but in this case, you just use some kind of the rule of thumb. So for instance, here I have variables for capital formation, natural resources rent, literacy rate, tertiary education rate, and secondary education rate. So obviously, secondary education rate is highly, or let's say strongly correlated with literacy rate. So in our case, correlation coefficient calculated using this formula is close to 1, which indicates rather high level of correlation. So the problem with correlation coefficients analysis is that there is no exact value, So usually we use the rule of thumb by saying that the value of correlation coefficient above 0.5 indicates high correlation, and if it's below, it's fine. So this is something you can see very frequently, but it's not really justified, you know. So this is exactly what you call the rule of thumb in econometric analysis. You just take some critical value because you need some critical value, and it looks like a reasonable critical value. At the same time, you can do some formal analysis. Probably I will show it to you in a second. Okay, here you have it. So in order to design correlation coefficients matrix, you have to highlight all the variables and then choose correlation matrix. Okay, and here you have it. You can try to present it in a fancier form, but you know, here the problem is that GRETL tends to round those values. That's why, you know, you get 0. In fact, it's not 0, it's very close. So this matrix is fancy, but it's not really illustrative, and this is what I presented to you. And if you want to do collinearity analysis, yes, then you choose collinearity option. Okay, so now let's discuss output. So this is the output, and you do not really have to understand all the details hidden behind this analysis. GRETL will highlight the problematic variables automatically. So as it said here, if the value of the critical value of statistics is above 30, it indicates strong and closely to exact linear dependence. And if it's between 10 and 30, it's moderately strong. Like ideally it should be below 10, but take a look. Actually here you have those problematic variables. So I mentioned this before, it's visible even here because there is extremely strong correlation between secondary education rate and literacy rate. And in fact, formal analysis, formal tests reinforce this point. So in practice, it means that you have to omit one of these variables in your regression model. So you cannot insert both of them because there is closely linear relationship between them, and this would violate the absence of exact collinearity assumption. So that's why when you do some pre-estimation test or pre-estimation analysis, it's kind of a requirement. It's kind of a requirement to check the presence of collinearity. And of course you can use common sense because, as I mentioned before, for some of the variables you can just use some human logic to identify the presence of exact collinearity. But formal test is also appreciated because, technically speaking, I wouldn't suggest that there is close to exact collinearity between literacy rate and secondary education. This is not something, you know, I can assess without any data analysis. So that's why, again, just to reinforce this point, when you submit your project, please do something like this, like analyze correlation coefficients or analyze collinearity, to make sure that there is no exact collinearity in your data. Okay, so if your model is designed nicely, so it's unbiased and so on and so forth, then you interpret the value of I as the conditional mean or expected value of y conditional upon the given or fixed values of the independent variable x1 and independent variable x2. So again, this is very similar to what we discussed before, but now you have to take into account the values of both x1 and x2. And when it comes to interpretation of the independent variable coefficients, I believe it's kind of obvious that this regression can be described as the linear function. So that's why in this case you interpret coefficient as the partial derivative of y with respect to the respective independent variable. So for instance, beta 1 will stand for the partial coefficient of y with respect to x1, it will tell you by how many units y will change in respect to 1 unit change in the value of x1, assuming that the value of x2 is fixed. Analogously, when you calculate partial derivative of y with respect to x2 and you obtain beta 2, you assume that the value of x1 is fixed. So proceeding to the specification bias, I believe it will be more intuitive if I explain it based on the example. So the example suggested in your textbook is the following regression model. So in this model, we assume that child mortality rate depends on female literacy rate and the value of GNI per capita in 2000. By the way, this model is not really good, so definitely there are better potential determinants of child mortality rate, but nevertheless, this is what we start with. So the logic is like this, higher level of income is associated with higher level of healthcare spending and better nutrition, which decreases child mortality rate, and female literacy rate can serve as the proxy, like bargaining power of females in the households and general level of expertise in the child care. So that's why we assume that higher level of female literacy rate will be associated with smaller value of child mortality rate variable. But nevertheless. Okay, so here we have this regression model. Here you can see the output. Please pay attention to the fact that for both variables, p-value is higher than 0.1, which means that these variables do not cause any statistically significant effect on child mortality rate. So in this case, if you wanna check whether all of the variables are relevant, you can try to omit the variable. So for instance, I will show it to you in a second. Okay, yes, okay, close. No, this is cross-sectional. Ordinary least squares, child mortality rate. Here we have it. So now test, omit variables. I don't know, I would like to omit GNI per capita, or maybe better female literacy rate. In this case, I will estimate the reduced or restricted model, but also you can use WALT test, which is based on a kind of a different methodology, but nevertheless. Both of them are appropriate, so they are pretty robust. Okay, so in my case, null hypothesis is that the regression parameter for female literacy rate is equal to 0, which means that female literacy rate does not cause any statistically significant effect on child mortality rate, and p-value is bigger than 0.05, which means that I cannot really reject this hypothesis. So the value of coefficient is indeed 0, and now actually I can try to check the restricted model. So here it is. So GNI per capita is still statistically insignificant. Nevertheless, p-value is significantly higher than it used to be. You can also pay attention to the fact that we have different value for constant. Like compare this value and this value. So basically, yeah. Okay, so now when I estimate my model based on GNI per capita independent variable only, this is my regression output. Okay, I know it may be kind of misleading because here you can see that this variable is statistically significant and here it was insignificant. But the difference is that the difference can be explained by the fact that actually I have some, okay, give me a second. I use this Excel worksheet to calculate the F-test. So the difference can be explained by the fact that I have some gaps in my data. And when I have two variables with different gaps for different periods, the number of observations was 97, and now in the restricted model is 204. So please keep in mind that this difference in the output is explained on one hand by the fact that we skipped the variable, which is statistically insignificant. Not statistically significant, I believe this would be more appropriate formulation in this case, but also by the fact that now I have more observations and I have more degrees of freedom. So please be very cautious about this. But nevertheless, it was fine, so now I can see that GNI per capita actually decreases child mortality rate, and this value of the coefficient is significant at 5% significance level. So, this is fine. Actually, it was good for the model to skip female literacy rate. Like, this variable can be potentially important theoretically, so you can justify the use of this variable by explaining that more educated females can take care of their children in a better way, which decreases child mortality rate. But nevertheless, what data say is that this variable is kind of useless. So coefficient of the variable is not statistically different from 0, and it makes no sense to insert this variable to the regression model. Alternatively, you can use joint significance test, and here you can find the formula. So basically, here you have this indicator, sum squared residuals, which comes from restricted model. And I mean, this is the model which was estimated after I omitted one of the variables. Sum squares residual coming from unrestricted model, number of linear restrictions, so I skipped one variable, I omitted one variable, that's why Q will be equal to 1, N stands for the number of observations, K stands for the number of independent variables, and 1 is 1. So if you use this formula, you can calculate F statistics, and by using GRETL calculator, here tools, p-value finder, so here you can compute p-value for different distributions. I made sure that p-value is definitely smaller than 0.05. So zero hypothesis states that both coefficients are equal to 0, and it's not true. So actually, when it comes to GNI per capita, it turned out to be statistically significant. So that's why in this case we can reject zero hypothesis. So speaking very informally, joint significance test is just a test for significance, not for one variable, but for combination of several variables. Okay, so as you remember, we used R squared as the measure of model fit. So as we discussed, higher value of R squared is associated with bigger proportion of the explained independent. Okay, so as you remember, like as we discussed before, R squared is commonly used measure of model fit. So speaking informally, it presents the proportion of the explained variation out of the total dependent variable variation. So obviously, the more independent variables you add, the bigger will be proportion of explained variation, and accordingly smaller proportion of unexplained variation. But the problem is that there are many potentially important determinants when it comes to any of the dependent variables. So for instance, when it comes to child mortality rate, you can also think about number of doctors per 1,000 of inhabitants, I don't know, yeah, probably like quality of nutrition, climate, and so on and so forth. But the problem is that although adding these variables would increase the value of R squared, it's definitely not in line with the general idea of econometric modeling. So econometric modeling is all about defining the key relationships in the variables. So in this case, adding more variables in order to increase the value of R squared is not a fair play. So in the regressions with multiple regressors, we used adjusted R squared in order to address this bias. So it's calculated as the product of R squared. So you remember the formula for R squared, at least I hope so. And the difference between 1 and the ratio of k and n, where k stands for the number of parameters and n stands for the number of observations. So in this case, adjusted R squared will increase with R, but decrease with the number of parameters, which would produce more realistic measure of the model fit. So for instance, you can see this model, you can check this model output. So in this case, I took the number of healthy years of life as the dependent variable, and health personnel, like number of doctors per 1,000 of inhabitants, and health expenditure as independent variables. So as you can see, there is a difference between the value of R squared and adjusted R squared. And adjusted R squared is smaller. In this case, this gap is not that big because I have only two independent variables, but it would increase as the number of independent variables increases. So please keep this in mind, and when you analyze model output in the model with multiple independent variables, please take into account that you have to concentrate on adjusted R squared, not on R squared itself. Okay, so that was it, and I thank you for attention.